Hi, lab partner. It's time to finish the lab. Let's get going. All right, I'm going to shake myself down just a moment. Here we go. All right, so we are now ready to do the spoiler alert part of the lab. And so the very first thing is to look up the pendulum equation for period on your equation sheet and write it down. Well, guess what? I'm going to be your equation sheet today. So I'm over here, and I'm actually going to use the draw menu in Word to do this. I don't want you to type it out because there's a square root in it, and typing it out is going to be ugly unless you use the math type function to make it look very formal and beautiful. Otherwise, either draw it on a piece of paper and take a picture and insert the picture in here, or do what I'm doing, which is using the draw function. So the pendulum equation goes like this, that period equals 2 pi. Pi always takes me a minute to draw. Okay, square root of length divided by g. So that's the pendulum equation. Okay, now the first thing we're going to do with this pendulum equation is actually substitute in 9.8 for g and simplify this. Okay, so I'm going to change my pen colors just so you can see. Whoa, that's really a wide pen. Let's make that smaller. Thank you. Okay, so let's do this. We're going to substitute in 9.8 where g is. So I'm just going to work to the side. You can do this by hand on a piece of paper and then take a picture and import it into your file. But here I go. So I'm going to have here t equals 2 pi. You get to watch me draw. 2 pi again. Square roots of L. So we're going to keep the letter L there, and then over 9.8, and then the units, meters per second squared. Always keep your units in every number for the class when possible. Okay, now what I'm going to do is a little bit of math shenanigans. That actually equals t, well, it still equals t, and then I'm going to do this, 2 pi over the square root of 9.8 meters per second squared. Okay, so I'm just moving. Oh, that's a hideous. I'm drawing this with like my mouse and stuff. This is terrible. Okay, so I just took the 9.8 meters per second squared that's in the denominator here and moved it over, okay? And then what's left times is the square root of L. But I'm going to write this kind of on the side. The square root, does that even look like the square root of L? That's what the square root of L actually is the same thing. So reminding you as L to the 0.5 power. So L to the 0.5. So I'm going to, instead of writing it as the square root of L that's left, I'm going to say times L to the 0.5. All right. Then, oh, it's like a dramatic 5. Okay, what I'm going to do is to find my calculator here. So I have my calculator, and I'm going to calculate in my calculator. Literally, I'm going to type in 2 pi divided by the square root of 9.8. So I'll show you this very old-fashioned, look at my calculator, class, da la la. Okay, but I ended up with 2.007. Okay, so that simplifies then to t equals 2.007 L to the 0.5. Okay, so my challenge for you is that you're actually going to do the same steps yourself, which might sound silly, like, I just watched her do this. Why do I have to write it down again? It's really good for your memory because we're going to be doing this often with our math models in the class, substituting in things, calculating. So go do it yourself. See if you also get the 2.007 L to the 0.5, and then take that handwritten stuff that you did and take a picture of it and put it in the file, or use the draw pen like I did to do it. Okay, just don't type it in again because it just is awful. Okay, so Now that we have that, we can start answering a few more questions. So that was number 1. What do you think it means that the model only has the length variable inside? Okay, so answer that question like, what does that mean for length? Does it mean length is correlated or not? What does it mean for angle, that angle doesn't show up in the equation at all? What does it mean for mass, that mass doesn't show up in the equation at all? Okay, then does your model have the same function as a theoretical model? What function is this? It's a power function. So is your model a power function? So you just answer, hey, my model is a power function, the official model is a power function, they match. Or maybe my model was linear, this one's a power function, they do not match. So it's a very easy question. So go ahead and pause actually and answer that question, number 3 and number 2. Okay. Now, for 4 and 5, there's 2 routes you're going to take. If you got power function for length, you're going to answer the questions as written. If you got a linear function for length or a logarithmic or exponential or something else, you are going to answer number 4 and 5 a little bit differently. So I'm going to quit my drawing here. So let's say you got a linear function or something different. You just say for 4 and 5, my function was linear, does not match, so I cannot compare my numbers. Okay, that's legitimate. That's mathematically really a smart thing to say, because if you have a different function than the theoretical, you shouldn't be comparing the coefficients or exponents or anything. Just say my function's different, I can't do this comparison. That's legitimate. But if your function is the same, okay, like mine up here, I highlighted here, is a power function, then for number 4, which is asking, does it have the same coefficient? Well, this is 2, mine is 0.5, so I would say no, and then make sure you actually say what your coefficient is. And spell coefficient was 0.546, while the theory said 2.007, they are different. Okay? How easy is that? But make sure, take the time to actually write the numbers in. Answer that same sort of thing, but this time for the exponent. Again, if your model's different, you would write my model is a different function. It doesn't make sense to compare the exponents. All right, so let's pause now and answer 4 and 5. Okay, big deal here. I am not going to ask you if knowing the final answer has affected your confidence, because at this point, after the spoiler alert, our science becomes fake. Most of the time when you're doing real science, you don't know the answer yet. So you wouldn't have like a theoretical one to compare yours to and have confidence in. Real science is when you're finding a model and you're not sure if it's right in the end. You use your error bars and R-squareds and other things to kind of support your answer, but you'll never know 100% if it is correct in the real world. And so that's why I'm not asking you how this affects your confidence. Okay, let's see how we can finish up the lab. Why do you think your model isn't a perfect match? List 5 things that can be considered errors. So tell me about how your lab went here. Were there mistakes? Like, was your pendulum acting a little bit funny? What are all the little things that bothered you as you were taking data where you were like, you know, I don't think I'm doing this quite right. Or I could be doing this better if I had this piece of equipment or that. Tell me those things here, okay? Why do you think your model isn't quite the best match, okay? And then also, if you're making the backyard swing that has the largest period, what variable do you need to worry about the most, right? So if you're making a swing, which of the variables to make that period change is the most important? And are there variables in your backyard swing you don't need to worry about? What are those? This question is just kind of fun. It puts it in an everyday context. Like if you were actually building a swing, what matters? Do you have to worry about how heavy the board is that you're going to sit on? Do you have to worry about how long the rope is? Do you have to worry about what angles the thing can swing at? Are those things you need to worry about or not? So that's my very last question. And then at the very end, there's a little survey because we're always trying to improve our labs. So I'd really appreciate if you could answer those questions for me. Thank you. And great job, lab partner. You've finished Pendulum 3. Congratulations. This was a 1, 2, 3 lab teaching you all of our lab skills. And so our future tough labs are actually complete reviews of this lab just with different situations. So way to go. You've gone through it the first time. The first time is the longest and toughest. And just great, great job. And as always, if you have questions, send them my way. I am so here to help you. And thanks again for being a really awesome lab partner. Bye.